Hello everyone, I'm Parham Oveissi, and today I'll be presenting my work on model-free dynamic mode adaptive control using Matrix RLS. We conducted this research under the supervision of Dr. Anki Goel at UMBC. A huge challenge when dealing with complex systems, such as fluid flows, combustion processes, high-dimensional structural systems, is the lack of control-oriented mathematical models. And although high-fidelity computational models can accurately predict the behavior of these kind of systems, but these models are pretty expensive and are not well-suited for direct control synthesis. And that's why that has led to the development of data-driven model-free control approaches. Although there are multiple model-free data-driven approaches available, like RCAC, initially developed at University of Michigan. We also did a lot of work on that. The newer version of that, PCAC, and also other techniques such as MRAC and RL, but they all kind of show some limitations in terms of high computational costs, sensitivity to the tuning parameters, limited guarantees, and heavy training in the case of machine learning approaches. In this work, we proposed a model-free data-driven approach called the dynamic mode adaptive control. It is inspired by dynamic mode decomposition, or DMD, and basically it approximates a low-order model of the system, and then iteratively refines the controller. And in this work, we actually use a recursive version of the Matrix RLS to find the low-order model. And this technique is shown to be so efficient, pretty fast, and implementable in real time. Okay, let's set up the problem for DMAC. Let's consider a system which is evolving in continuous time. We can sample this system at discrete times by a fixed sampling time Ts. And the goal of DMAC is to generate a discrete control signal UK, which ensures which makes the sample output of the system to track the reference command RK. And the control input is implemented using a zero-order hold mechanism, which means that in between the samples, the control signal is kept constant. And this setup basically forms the foundation for developing DMAC, which combines the dynamic model approximation as the first module, and a controller and an adaptive control synthesis as the second module. So it basically has two different modules. The first module, let's focus on the dynamic approximation. Basically, in this module approximates an online model of the system, and it actually approximates it in terms of a status space representation. And we do that using the sparse measurements available from the system, and that's what we call as squiggly. Squiggly is the measured portion of the state. It could be the entire state of the system or just a subset of it, depending on what sensors are available. And we can equivalently write it in the regressor form, shown as in this equation, where theta is a big matrix containing AB matrices, and our goal is to basically find these AB matrices. And there might not be an exact solution to this problem, but we can always approximate that using a cost function showed below. And in this cost function, the lambda is the forgetting factor, which basically ensures that the algorithm it basically prevents the algorithm from sleeping. So it makes the algorithm to be more responsive to the changing dynamics. And also, we do have the R theta, which is a regularization term, which makes sure that the optimization problem is well posed and it avoids overfitting. I want to make a connection here with the dynamic mode decomposition. As I mentioned at the beginning of the presentation, DMAC is inspired by DMD. DMD was initially developed by in the fluids community. They use that for reduced order modeling, and what they do is that they basically take the snapshots of the states and the inputs to the system, and they call them state or input snapshot matrices. And they are also looking for the linear maps A and B, and they write it in the same way. And if you look at the cost function that we're using is basically the same cost function as DMD. So mostly they do it offline, but they have also some online versions, such as the Windows DMD, which kind of can handle some time-varying system problems. So this is DMD, but DMD mostly focuses on reduced order modeling, doesn't inherently do any controls, and we were like, why not add controls to it? So getting back to the cost function, solving that cost function every time from scratch, it would be so time consuming. So we came up with a recursive update formula for that, which is basically a matrix version or a matrix implementation of the recursive list of squares solution. And then you can see the recursive updates of theta k, which is a matrix, the matrix containing our AB matrices, and the recursive update of the covariance matrix. And the key features of these update formulas are, again, the forgetting factor, and also in order for the solution in order for the estimates to converge and for the corresponding covariance matrix to be bounded, we need persistent excitation, and that's why you will see when we get into the control part, we actually add a probing noise, which is a small zero mean noise, to the control signal to make sure that we do have the required the excitation for our algorithm to converge. Okay, getting to the control module, it's a simple full state feedback controller with integral action, and when I say full state, I'm talking about that measurable portion of the state. So I'm talking about a squiggly. When you're dealing with a system, it might not be the actual entire state of the system. So where we have the first equation basically shows the full state feedback controller structure. As I mentioned, we do add that probing noise Vk. It's a zero mean noise in order to make sure that we do have persistent excitation in the system, so that our algorithm, the RLS algorithm, converges. And we do have the K squiggly K, which is the adaptive full state gain, and the KQ gain, which is the adaptive integral gain, and QK is the integral state, which is basically the cumulative error. Okay. So let's start looking at some numerical examples. We'll start with a very simple system. You're all familiar with that, mass spring damper system. And those are the parameters of the system we're using in these simulations. And we're starting from zero, so we have no idea of what AB matrices are. And these AB matrices are being updated online and using that matrix RLS that I mentioned. And here we're dealing with a simple problem. The reference signal is just 1, and the hyperparameters of the adaptive algorithm are given. The forgetting factor, the R theta, the regularization matrix, and all. And as you can see, the first plot, like on top, the top left corner, shows the output of the system. It actually basically tracks the reference command, and then you can see the control signal on to the right of it. And then on the below, you can see the absolute value of the error. And at the beginning, you can see like it's kind of doing the learning process because it's it starts from 0, and that probing noise helps the system to get some excitation, so we get a better understanding of the model, we get a better approximation of the model, and then the controller kicks in and drives the output to the desired reference. And then we do a robustness study on that. We want to see how robust this technique is to the tuning parameters as well as the system parameters. And you can see on the top right corner, we are demonstrating its robustness, the robustness of this technique towards the tuning parameters. We can change them in multiple orders, and in all cases, still we were able to follow the reference command. And then at the bottom, you can see the robustness of this technique towards the system parameters, those MCK. We were changing those variables to see how that affects the algorithm. But this was the case where we considered like the full state of the system, the two states, and in the next example, we consider the 3-mass spring system. But in this case, so we have like 6 states, but we're saying, okay, let's say we can only measure those 3 states, Q1, Q3, the positions of the first and third mass, and like the velocity of the third mass, the first mass. So we are basically here we're approximating the whole system with a third order system, and we get basically 3 by 3 matrix. So again, here you can see on top, the problem again is a simple reference tracking of 1. And then you can see in the top left corner, the output is basically tracking the reference command. And you can see the UK, also the error this time, the absolute value of the error is shown in the logarithmic scale, and it's just going down. And you can see the theta, which are those parameters, or basically the values of AB matrices, they are converging. We also did the robustness study here, both for the system parameters as well as the tuning parameters of the algorithm itself. And you can see again in all these cases, we are able to track the reference command. Okay, let's get into a nonlinear system, the Van der Waals oscillator. Again, here we are considering the case that we have access to the move states, Q and Q dot, and again, the system parameters are given at the beginning, and then you can see the tuning parameters of the DMAC algorithm. And as you can see, the absolute value of the error on a logarithmic scale is just keeps going down. And again, you're able to track the reference command. And again, we do the robustness study. And as you can tell from the example, this was more like a tutorial paper, like showing the basically showing the idea. Our main application that we're applying these techniques, and we have applied it so far, are flow control problems like gas mitigation for wind tips, or frost regulation of solid fuel ramjets, combustion processes, and that's what we are actually looking for. And these are more like tutorial-based examples here. The next example you can see it's the Burger's equation. It's a PDE, and in order to solve this, we basically discretize the domain into discrete nodes. And for this example, we have discretized the given domain into 100 grid points, and we are assuming that we have some sparse measurements of this system, and these are the nodes that we selected for the states, and these are basically the 7 states of the system that we use for DMAC. And next, you can see the results here. So we select one of the nodes, like node 55 out of those 100 nodes, in order to apply the control signal to it. And then you can see again, in this case, this is like a high dimensional system. We are approximating it with a 7-order system, and then we apply the control signal to node 55, and you can see it's able to track the reference command. And again, all those data values are converging. It's running out of time. Again, we did the robustness studies. Believe me, it worked with all the hyperparameters and system parameters. And then finally, so we developed this technique, DMAC, which basically combines a low-order model approximation inspired by DMD, and then it combines it with an adaptive reference tracking control approach. And then we demonstrated that on multiple systems. And in future work, we are working on reducing the probing signal requirements. Also, we are looking for some constraint optimization for stability to make sure that those AP matrices that we're getting are always controllable. And also for the journal version, we have worked on the theoretical guarantee, the Leopold proof sound, which will be in a paper. So thank you so much.
For what question? There's no question. Yeah, please.
When you have a complex system like flow control, how do you define the dimension of the system, the linear?
Oh, so it depends on the sensor that are available. For example, we did a work with NCSU. They have an actual SFRJ experiment, and we just asked them, so what kind of sensor do you have? What data can we use? And we just use that sensor information, and we just said, if they have, like, let's say 3 sensors or 4 sensors available, they usually have multiple pressure sensors along the way, and we use those data as the state vector, and we construct a model based on that. Yeah.
Thank you.
All right. Thank you. Appreciate it.